Hi everyone, we are talking about the second fundamental theorem of calculus today. So let's take a look at what we have and see how it's different. Okay, so we have the derivative of an integral of t squared dt. So far it doesn't look too bad, except one of my bounds is a variable. We haven't seen that before. So let's actually evaluate this and see what happens. Okay, we're going to start from the inside and work our way out, okay, kind of like PEMDAS. So you might have kind of an expectation of what's going to happen because I'm taking the derivative of an integral. They're kind of opposites, right? So you might have an expectation of what's going to happen here. So the integral of t squared is going to be 1/3 t cubed from 1 to x. Okay, and I'm going to do the first fundamental theorem here. So I have 1/3 x cubed minus 1/3. Okay, now I'm going to take the derivative. So I take the derivative of 1/3 x cubed. Well, that's easy. That's just x squared. Derivative of a constant goes away. So let's take a look at what we have. I got x squared as my answer, and my integrand here, or what's inside my integral, is t squared. So notice what happened. Hey, let's make sure this isn't a freak accident though. Let's do it again, see if there's a pattern. So again, we're going to integrate cosine. So I'm going to differentiate later. The integral of cosine is sine from pi over 6 to x. Okay, let's do the first fundamental theorem. So I have sine of x minus sine of pi over 6. Do we have to evaluate this? No, because we're going to take the derivative. So I take the derivative of sine x and I get cosine of x. Derivative of this situation is constant, goes away. So again, cosine of x, and I started with cosine of t as my integrand. So hopefully you noticed a pattern there. If you were taking the derivative of an integral of a function from a to x or some variable, you're essentially going to do a variable swap. You're going to end up back where you started from. We're going to end up with the same function, except my variable is going to change. Okay, well, this one looks the same, except my bounds are flipped. So you probably guessed what's going to happen. I'm going to go ahead and use my integral rules and switch my bounds. I'm going to flip it. Right, so that's going to make the whole thing negative. Right, so this time I flipped it and I got a negative, or I flipped my bounds, or I switched the direction that we're integrating, whatever, however you want to think about it. Right, so same deal. I know that the derivative of my integral here is going to result in just x squared, and I have a negative there. So negative x squared. Right, so that's going to be a general rule. So let's write this as a rule. You can always just flip your bounds, and then do your variable swap, and it'll end up negative, meaning you're going to change the sign of every single term. Okay? Every single term you're going to change the sign. Let's keep going. Okay, now what's different? Well, I have a whole function here. I don't just have a variable, I have an x squared. It's a whole function. So let's go ahead and go through the process again, see what happens. I integrate cosine, I get sine, and you might be able to guess what happens. When I do the first fundamental theorem, oh sorry, this should be a t, that's my mistake. I do the first fundamental theorem. Okay, now when I take the derivative, look at what I have here. Again, this is a constant, that's going to go away, but look at what I have here. I have a composite function, and what do we do when we differentiate composite functions? We do chain rule. Do not forget to do chain rule. So if you have a function, as your bound instead of a variable, all you have to do is remember chain rule. So notice how the first part of my answer here, it's the same thing that we did before. All I did, instead of cosine of t, I ended up with cosine of x squared because that's what I have here. But I had to remember to also take the derivative of my upper bound here and add that at the end because of chain rule. Right, so same thing. Essentially, it's the same thing. So here, all I'm going to do is sort of substitute t for g of x. Okay, that's what's going to happen. And I have to remember to multiply by g prime of x. Say, or if you prefer a different notation, you could think about it as this, and you're just swapping. So instead of, I don't know, a to g of x, maybe a to u is more comfortable for you. So we get f of u times u prime. That's kind of funny, I just noticed that. Okay. So a big thing to notice is even if you had no idea of what was happening, it kind of doesn't make a whole lot of sense just by looking at it. Because keep in mind, we're differentiating with respect to x, okay, and we're integrating with respect to t. So that should tell you something. That should tell you where to start. Okay, we always have to start by integrating because I need to integrate with respect to t. Okay, there's no x's for me to take the derivative of. Okay, I have to integrate with respect to t. Then I get that x in there, then I can differentiate with respect to x. So that pretty much tells you the order of how to do things right there. Let's practice. Right, at this point, we should be pretty good. All we're going to do is swap my variables. Okay, so my function doesn't change. I have an x here. It's not a function, it's just a variable, so 1 plus x squared. Okay, next one. I have tangent of t cubed, but it's not t cubed anymore because once we differentiate, we integrate, and then we differentiate, we end up with x cubed. Okay, do I have to chain rule here? Not really. I mean, you sort of already are because the derivative of x is 1, but you don't have to write anything. Okay, this time I'm going to end up with a composite function. So okay, I do my variable swap, but I have to remember to multiply by the derivative of my function there, so 3x squared. Same thing here. Okay, I'm going to have the cube root of 1 plus sine squared. I also have to remember to multiply by the derivative of sine, which is cosine. All right, let's keep going. Now this is a very, 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 very common problem. Okay, you see this a whole lot. Okay, you have a graph of f, and then you're given this situation, which you should immediately recognize this to be the fundamental theorem, second fundamental theorem. Okay. Now they gave us the graph of f. They didn't actually give us f. They gave us g of x, which is equal to the integral of f. So if this is the graph of f and they gave us the integral, then we have to take the derivative to figure out the relationship, right? So if I take the derivative of g, I end up getting f of x, which is what they gave me. So they said they gave me the graph of f, but really they gave me the graph of g prime. This is a derivative graph. This is a derivative graph. This is a derivative graph. All right, let's solve some problems. So first, they're not really asking us to use the fact that it's g prime. They just want us to evaluate some points. So we can do that, right? First, they want me to find g of 0. Okay, well, I'm just plugging 0 in for x. So I have the integral from 0 to 0 of f of t dt. Now, we don't know what t is. We don't care what t is. We don't have to know what t is because we have this graph here. Sorry, when I said t, I meant f. Okay, we don't know what f is. We don't care what f is. But we're taking the integral from 0 to 0. So that's going to be 0. You can't take the integral of a line or something that's one-dimensional, or however you want to think about it. Next, they want us to find the integral of 0 to negative 1 of f of t. Okay, well, that's right here. So I'm starting at 0, and I'm going to negative 1. So I'm going backwards, so that's going to be negative. I'm going backwards, so I know it's going to be negative, and this is just a triangle with an area of 1. Next, g of 2. So 0 to 2, f of t dt. So this time I'm going 0 to 2. I'm going this way. Ignore this now. And this is going to be my quarter circle. So if you calculate the area, you find that this quarter circle has an area of pi. So that's going to be my g of 2. All right, last one, g of 5. Well, that's going to be 0 to 5. Okay, so that is going to be the whole thing. So I have to go even further now, all the way to 5. Okay, so 0 to 2 and 2 to 5, right? So we could split this up. You don't really have to, but I think it's a little easier to see it that way. So I see this as two shapes, one above the x-axis, one below. Okay, I have a quarter circle here. I have, I guess we could split this up again if you want to, but like maybe a triangle and a trapezoid or something, some weird trapezoid that's not right. Okay, some trapezoid below the x-axis. So I'm going to split this into two integral, 0 to 2, just to show my work, and then 2 to 5. Okay, 0 to 2, I already know that. That's what I found here. That's pi. Okay, 2 to 5. Well, again, this is going to be a triangle. So this is a triangle with an area of 1. We already found one of those. This is a trapezoid, a right trapezoid. So you could average the bases, multiply by the height. So you end up getting an area of 3 here. Okay, or you could look at this as 2 squares or a rectangle and then another, however you want to look at it. There's a million different ways that you could look at this. By million, I mean like 4. There's 4 different ways that you could really look at this. So I end up getting an area of 3 here. So altogether, from 2 to 5, I have an area of 4. Now keep in mind this is under the x-axis, so it's going to be minus 4. Fantastic. Next, they want us to find all values of x between -1 and 5, where we have a maximum. So I know that we have a maximum when we change from positive to negative, but specifically our derivative graph has to change from positive to negative, which is convenient because they gave us the derivative graph. Look at that. Look at that. So again, this is g prime, this is g prime, this is g prime. Okay, so I need g prime of x, I have g prime of x. So first of all, let's prove it. Okay, so I know I need g prime of x, but they didn't explicitly give me g prime. So I need to prove that I have g prime. So I know that g prime of x is equal to the derivative of, there. And this is just the second fundamental theorem. All right, so I know, what I just did is I established the relationship between g prime and f, because I have f. Okay, so if I want to use this information that I have to be able to connect it to what I want. Okay, I want a g prime, I have f, I connected them. Okay, well, I know that g prime of x changes from positive to negative at 2, because it goes from above the x-axis to below the x-axis. So I'm going to go ahead and say that. And I'm going to say this in a complete sentence. So g prime of x equals f of x, because again, I need to relate the two ideas. Okay, this is what I want, this is what I have. It changes from positive to negative at x equals 2. Okay, be very specific here. Okay. Next, they want us to find the absolute minimum. So we're going to do a candidates test. So remember, we have to check our endpoints. We have to check any critical numbers. I already know what my critical number is. It's 2. So I'm going to set up a candidates table here. Right, the points I have to check are my endpoints and any critical numbers. Critical number here is because my g prime graph passed through 0. And then here are my endpoints. So remember to check your endpoints. Okay, always remember that. Okay, well, luckily we already calculated these in part A. So at -1, I get -1. At 2, I get pi. And at 5, I get pi minus 4. Okay, I'm asking for an absolute minimum, so this is going to be my absolute minimum. So I'm going to write out the absolute minimum of g of x is -1, and it occurs at x equals -1. Okay, so this is my statement. Okay, this is just stating where my absolute minimum is. Now I have to justify it. So after x equals -1, g prime of x, which equals f of x, is positive more than it is negative. Therefore, g increases more than it decreases. Cool. All right, so what I mean by that is I know if you look at your graph, okay, so if you scroll up or just look up, you look at your graph and it starts right here. Okay, it starts right here, and I don't really know what's happening here, but I know it starts right here. Okay, and then I know it increases for a time, but then it also decreases. So the concern is that maybe it decreases more here than it increased here. Okay, and so that's what I addressed. So you could, I guess you could argue like 1 plus pi, which is how much it increased, is greater than 4, which it is. So I know it didn't go back down as much as, right here where I started. Or like I said, I just know that it increases more than it decreases because I didn't specifically say the values, but I know 1 plus pi is greater than 4. Okay, and they want us to find the x-coordinate of each point of inflection. Okay, so that is where my g double prime is going to change sign. And from my sign chart, or that little chart that I showed y'all before, this is also where g prime changes direction. Okay, this is where g prime changes direction. Okay, well, let's look at that. So I noticed that g prime changes direction right here. So I'm literally, because remember, this is g prime. Okay, so I'm literally looking at where my graph changes from increasing to decreasing. Okay, so I noticed that it changes here. It doesn't change here, and then it changes here. Okay, so I should have 2 points of inflection. I have 1 point at 0, and I have 1 point of inflection at 3, because that is where my graph changed direction. Okay, so I know that g prime of x, which equals f of x, changes from increasing to decreasing at x equals 0. Okay, g prime of x equals f of x also changes from decreasing to increasing at x equals 3. All right, those are my 2 points of inflection. All right, that is it for this video. I'll see you all later.